Hi guys, today I will be teaching you about rate laws. Reaction rates are dependent on the concentrations of one or more of the reactants, and the rate law expresses this relationship between the concentration of a reactant and the rate of a reaction. The rate law expression is rate equals K times the concentration of A to the power of N, where K is the rate constant, bracket A is the reactant concentration, and N is the reaction order. Reaction order determines how the rate depends on the concentration of the reactant. Reaction orders can be 0, first, or second, with n equaling 0, 1, and 2, respectively. When a reaction rate is zero order, n equals 0 and the rate is equal to K. The reaction rate is independent of the concentration of the reactant. The slope of the line is constant, indicating a constant rate. The rate is constant because the reaction does not slow down as the reactants are being consumed. Zero-order reactions occur when the amount of reactant available for the reaction is unaffected by the overall quantity of reactant. For example, sublimation is normally zero-order because only molecules on the surface can sublime, and their concentration does not change as the reactants are consumed. When a reaction rate is first order, n equals 1 and the rate is equal to K times the reactant concentration. The reaction rate is directly proportional to the reactant concentration. Because of this, the rate decreases as the reaction proceeds because the concentration of reactant is decreasing. The reaction rate and reactant concentration have a linear relationship because they are directly related. When a reaction rate is second order, n equals 2 and the rate is equal to K times the reaction concentration squared. The rate of the reaction is the square of the reactant concentration. Because of this, the rate slows down even faster as the reactants are consumed. Because there is no way to tell how fast a reaction will proceed by looking at a balanced equation, it must be determined experimentally. One way is by using the method of initial rates, where the rate is measured at the beginning of the reaction and is ran several times with different initial concentrations. The following table shows varying initial concentrations of a reactant and their respective reaction rates. Look at the first two rows. The reactant concentration increases from 0.1 to 0.2 molar, which is 2 times 0.1. When you look at the reaction rate, it also doubles from 0.015 to 0.030. As the concentration is multiplied by 2, the rate is multiplied by 2 to the first power, indicating a first-order reaction. Let's try the following examples. In this example, as the concentration is multiplied by 2, the rate is multiplied by 4, or 2 to the second power. Therefore, it is a second-order reaction. In the next example, as the reactant concentration is multiplied by 2, the rate remains the same, or is multiplied by 2 to the 0th power. Therefore, it is a zero-order reaction. As you probably already know, reactions usually involve multiple reactants. The rate law for a reaction with two reactants is expressed by using the equation rate equals K times the concentration of the first reactant to its reaction order times the concentration of the second reactant to its reaction order. The overall order is the sum of all reaction orders. To determine the rate law, we must find the reaction order for each of the reactants. We do this by comparing rows where one reactant is held constant while the other is changed. For example, in the first two rows, the concentration of carbon monoxide has remained constant while the concentration of nitrogen dioxide doubles, ensuring that any difference in the initial rates is due to the changing concentration of nitrogen dioxide only. Looking at the same first two rows, the initial rate is multiplied by 4, or 2 to the second power, showing the reaction in second order with respect to NO2. Looking at rows 2 and 3, the concentration of NO2 is now held constant as the concentration of CO is doubled. The rate only changes a very insignificant amount, showing the reaction is zero order with respect to CO. We can use the integrated rate law to see the relationship between reactant concentration and time. When a reaction is first order, graph the natural log of the reactant concentration versus time. If it is second order, graph the inverse of the reactant concentration versus time. If it is zero order, simply graph the reactant concentration versus time. By graphing these, you can find the rate constant K by using the line slopes. The following are ways to find the y-intercepts. Finally, I will be talking about half-lives. A half-life is the time required for a reactant concentration to halve. From the definitions of the half-life in the integrated rate law, the expression for the half-life of a first-order reaction is 0.693 divided by K. Keep in mind that half-lives are independent of initial concentration. I hope you enjoyed this video about rate laws. Thank you so much for watching.